Why do fluids flow? What governs their behavior? Why do they run smooth? Why are they turbulent? Are liquids the only fluids? Under certain conditions, gases and liquids behave like one another. Both are fluids. Two distinct forms of fluid motion which occur in nature are of crucial importance to the chemical engineer. They are laminar and turbulent flow. Fluids flow under the influence of a force. The character of the flow depends on this force, also upon the nature of the fluid, the shape and size of the channel in which it is held, or the path along which it must travel. Consider the simple example of water flowing slowly in a pipe. The streamlined flow of water can be represented by a series of concentric rings. The center ring moves some distance forward. Those next to it progressively less, until, next to the wall of the pipe, a molecular layer is reached which does not move at all. When a fluid moves slowly along a pipe, it follows this pattern. It moves in concentric layers. This is called laminar flow. Fastest at the center, progressively slower towards the wall. The shape taken by the layers is called a velocity profile. With laminar flow, the profile is always a parabola. The slow, steady flow takes place with the concentric layers exerting a force on each other, known as drag. The total of the drag imposed by the wall is known as the viscous force. Changes in viscous force are produced at different rates of flow. The viscosity of a fluid depends on its molecular cohesion. Syrup has a higher viscosity and spreads more slowly than oil, which is of a lower viscosity. Or milk, which has a lower viscosity still. But irrespective of viscosity, any fluid in motion possesses another characteristic known as inertia. This inertia tends to keep the fluid moving in a straight line. So viscous force retards motion and inertial force maintains it. It is the ratio between the inertial and viscous forces, known as the Reynolds number, which governs how a fluid will flow. Several factors affect the Reynolds number. It increases, for example, if the fluid velocity is increased, or the density, or a wider pipe is used, or if the viscosity of the fluid is reduced. The Reynolds number can be low or high. When the Reynolds number for a circular pipe is below 2,500, the flow is laminar. When it is higher, the flow becomes turbulent. A simple experiment shows how water behaves when flowing at different Reynolds numbers. Blue dyes, released within the flow, make their journey in separate, orderly paths. They move with the fluid in streamlines along the pipe. If a greater quantity of fluid is allowed through the pipe, the flow velocity increases, and the flow pattern becomes disturbed. All that remains of the previously smooth flow situation is now confined to a laminar sublayer along the walls of the pipe. The release of pulses of blue dye across the laminar flow stream shows how the viscous forces produce a velocity profile in the shape of a parabola. As flow rate is increased, the fluid becomes turbulent. When more than one color dye is introduced, the effect of turbulence is seen even more clearly. Increasing the fluid velocity increases the inertial force, raises the Reynolds number, and turbulent motion takes the place of laminar flow. Reduce fluid velocity, the viscous force again dominates, and with a lower Reynolds number, laminar flow returns. The observation of laminar and turbulent flow has led chemical engineers to an understanding of many of the principles underlying important branches of modern technology. One of the more important studies involves fluid flow around obstacles. Liquid flowing past an object exerts a drag force. At a low rate of flow, this drag is very small. As the flow rate increases, so too does the drag, and a turbulent situation develops. When the total force exerted is greater than that holding the object in position, it is swept away. As with liquids, so too with gases. The airflow in the tube is strong enough to support an object. As flow rate is increased, so is the drag force. Finally, the object is ejected from the pipe. It is these principles that apply in industrial processes when gas or liquid is introduced between particles of solids. If at several points a fluid, which could be gas or liquid, is introduced into a volume of solids, the forces determining the flow are similar to those acting on a fluid in a pipe. Laboratory experiments provide evidence that in its journey between the solids, the gas or liquid may be in either streamline or turbulent flow. Two different kinds of solids, beads and powder. One is suspended in gas, the other in water, and they both behave in the same sort of way. The solids resist the flow of the gas or liquid. But if the flow rate is high enough, they will become fully suspended in the fluid as a result of drag forces acting upon them. The solids can now be handled like a fluid. This state of suspension is known as fluidisation. In suspension, solid particles circulate in random motion. In this state, their entire surface is exposed. This is an important factor in many industrial applications. A good example employing fluidisation is in the rapid freezing of food, where heat exchange is so efficient that the outer surface of the vegetable is frozen almost immediately, and the remainder within minutes. A technique which depends on the characteristics of a suspension of particles behaving as a fluid. In flow, liquids and gases follow similar laws. They will flow only under the action or influence of a force. The path along which they must travel, the shape and size of the channel in which they are held, the nature of the fluid decides whether the flow is laminar or turbulent. By observation and the study of these laws, the technologist can condition and change our world, just as nature has fashioned it in the past.